Now let's get started with our session. We'll have time at the end of the session for a few questions. You're welcome to submit questions via the mobile app, the session catalog, or you'll be able to ask at one of the microphones in the aisle at the end. Please welcome Arthur Mensch. Arthur is CEO of Mistral AI, which trains state-of-the-art generative models with a strong emphasis on customization and control. He'll be speaking to us today about lessons learned while training their first models, Mistral and Mixtral, and give us a glimpse of the year ahead as well. Welcome, Arthur.
Is it working? Good afternoon, everyone. So I'm CEO of Mistral AI, and I'll effectively give you a bit of the overview of what we've built so far and also where we're coming from. If that goes, but before I actually present like the company and where we are differentiating and the kind of models that we intend to build and that we have already built, I wanted to give like a couple of like our vision of what happened in the last 2 years for language models and how that evolved in between, I guess, GPT-3 2019 to where we're standing today with basically assistants that can be deployed on laptops. And so I will try to explain how I saw it unfold, and because I think it's a pretty interesting story. So if you look at basically what kind of LLM you could tame into a useful assistant, which is, if you, as a scientist, you can say that it needs to be higher than 60% on MMLU. That's typically below that, it's not useful enough, and it's a bit frustrating. Beyond that, you start to be interacting with like an assistant or a companion, which is good enough and clever enough. Well, if you try and look at the sizes of the model that we saw matching this kind of performance. Well, in 2019, actually, GPT-3 wasn't at 60% MMLU, but it was good enough, not far away. I was at the time in 2020 at DeepMind, where we did a paper called Gopher, which was actually bigger, and that actually reached the 60% MMLU threshold. And then NVIDIA was at the time, so in 2020, there was somehow a race toward making bigger and bigger models with all of the infrastructure challenges that were associated to it. So you had to do pipelining, you had to do tensor parallelism in basically every directions. And we went to a point where I think that was NVIDIA that released this 530 billion parameters model. And then suddenly in 2022, the same kind of performance was achieved by a model which was much smaller. And I'll explain how we actually got to that. So that was at DeepMind. And so at that point in time, I think there was a realization that we didn't need to go to have very big models, and that it was probably not such a great idea. And if you look at what happened, so in 2022, you had ChatGPT that happened, very linked, I guess, to the fact that Chinchilla paper actually corrected the scaling laws. And then we kind of continued in that direction in 2023 with Llama 2 from Guillaume, Timothée, my co-founders, many people at Mistral today. At that point, you see like this interrogation marks that basically says that the field entered into some form of opacity in the technology at use in the technology used by the different providers. And this is something that kind of kick-started Mistral and the reason why we created it. And what we focused on is to try, like the goal of Mistral at the beginning when we started the company was to get to 60% MMLU with a model that could run on a laptop, and that's how we got to Mistral 7B. And so what's interesting there is that there's basically a factor of 40 in between like Gopher, which was the first model that achieved that performance, and Mistral 7B. So that was the premise of how we started, and I think that I'll explain how that I believe this is opening a lot of avenues for like interesting applications. So it's kind of a biased slide because it ends with Mistral 7B and Mistral 8X 7B, but there is a trend there, and I'll try to explain exactly how that happened from a scientific perspective. So in 2020, the trend was to make those models infinitely big. And I guess the starting point for that was a paper from Kaplan and Al from 2020 that came with this conclusion that if you were doing like a 10 times training, if you had a 10 times training budget, so if you were to go from like 1 week to 10 weeks training over a cluster, well, you should allocate that to 5 times the model size and 2 times the data. And as it turns out, the compute that you spend on is basically the multiplication of 2 factors, so the size of the model and the size of the data. And the conclusion of Kaplan was to say, well, if you go to infinity, you need to have an infinitely big model that is trained on an amount of data which is much smaller. So this premise pushed like basically the entire field to train models that were bigger and bigger on the same amount of token, which happened to be 300 billion tokens. So for 2 years, everybody were training models on 300 billion tokens. And it kind of slowed down the field a bit, because at some point, if you train your model on 300 B token, you start saturating because you don't see enough token. Start overfitting your data set. And so that was a problem that we started to observe back at the end of 2021. And so we noticed this problem, and I guess the answer to this problem was you needed to train on more than 300 billion tokens. The way we approached the problem at the time was to say, okay, you have a certain compute budget. The compute budget is the number of parameters times the number of data points. And so how do you actually make the appropriate trade-off in between scaling your compute, scaling your model size, and scaling the amount of data? And as it turns out, and it's kind of obvious in insight, but it wasn't at the time, is that if you do have like a 10 times training budget, you should basically multiply by square root of 10 the model size and square root of 10 the data. And that's actually the only setting in which doesn't explode when you go to infinity. So that basically tells you that if you have an infinite amount of compute, you should scale at the same speed the size of the model, so the capacity of your representation, and the amount of data points on which you train on. So that means that your compression factor should somehow stay relatively constant. And as it turns out, it's approximately like the optimal compression factor is around 30 tokens per parameter. So if you have a certain compute budget, whatever you do, and it kind of depends also on the quality of the data, but you need to run at 30 tokens per parameter. So that was a good insight. But somehow it also like directed the field toward like a bad representation where everybody started to think that models should be Chinchilla optimal. That was a term coined, I guess, on Twitter. And except that if you're Chinchilla optimal with a 7B parameter model, you're basically training on 200 billion tokens. And the model that you end up with is like at chance level on MMLU, and it doesn't work at all. So like this is compute optimality is not great. Training compute optimality is not great if you want to make models that can run on laptops. And so I think something that then like approximately 8 months later, there was the Llama paper, the Llama effort from Meta, that actually showed, I guess some people knew it before, but that showed to the world that you should actually train your model probably more if the model was small. So Llama 7B was probably the first 7B model to be decent and to have good performance. And the reason why it was performant is that it was trained like 3 times more than the compute optimal regime that Chinchilla was advocating for. And so I guess what it was saying is that if you have a 10 times training budget, you should consider your inference budget when you make your choices in terms of architecture. So if you only consider your training budget, then you should be training something, that gives you like 30 tokens per parameter. But if you take into account the fact that you're going to deploy your model on many GPUs, you should try and make your model smaller. So you should, the more you train, the more token you see during training, the smaller the model can be for the same kind of performance. So you invest some compute at training time to compress your model more, and that's, I guess, one part of the recipe that we apply to get to Mistral 7B. And so in that sense, I think it's useful to consider this kind of graphs where you compare the model size to the amount of training flops that you should be applying. And here what you see, the line, like a single line is basically points that have the same loss. And the loss is indicative of the performance. And what we call Chinchilla optimal at the time is basically the point where you have an horizontal, well, you have the point where you have an horizontal tangent, and these were like the Chinchilla optimal models. And then if you say that, okay, I have this model, but I would like to make it smaller, and so I want my model to be the same loss as the red point, but I want it to be smaller, I'm going to pay more and more compute. So as you move from on the y-axis there, you're paying more compute. So you're paying more dollar to your cloud provider, or you're buying more GPUs. And at the end of the day, here you can make like a very strong improvement. You can move from something which is 100 billion parameter to something that is approximately 10 billion parameter. So there's a cost of compression there, and I think that's a very interesting phenomenon, and it's very predictable in a sense. You can measure it. You can measure it empirically, and that's I think that's a very important graph because that sets the economics of this period. Basically, you need to invest a certain amount of compute to get to a certain size, a certain compression level, and that's what you should be optimizing for when you're running a foundational model company. And so I think the like for the mathematician in the room, the loss here is basically defined by like a certain term that you can't get under, which is called the natural entropy of the text. And then you have two terms. You have a term that depends on the size of the model. So the larger the model, the more representation capacity you have. So you can lower the loss by increasing your representation capacity. But then you pay something that is linked to the fact that you're doing stochastic gradient descent, and which is basically a stochastic noise term that is dependent on the number of tokens. And you have these two things that tells you that to lower the loss, you can either increase the weights or you can increase the number of tokens. And that's by just plotting this kind of this kind of loss, you end up with such a graph, and that's the one that sets the choices you should be making during training. So if you put that into practice, and that's really what we did when we started the company in June, you end up with a model that can be much better than Llama 2 7B. And so that's how we got to Mistral 7B. We really pushed the compression as much as we could. And we ended up with a model that was outperforming, Llama 2 13B at the time. And then we continued in that direction to get to a model which was called Mixtral in December, running only 12 billion parameters, active parameters, and having the same kind of performance than Llama 2 70B. So by pushing this compression and also changing architecture, we went to, we gained a factor of 5. Compared to the existing state of the art. And when you gain a factor of 5, it's pretty cool because you can deploy it on laptops and you can basically run it 5 times more. So that's an important parameter to take into account, and it also explains like the movement that we observed in various companies in 2023. So that's what we did. That's the kind of observation that we had when we started the company. We wanted to be efficient and we wanted to be open source. So that's we released Mistral 7B in June. We released Mixtral 867B in December, and we're continuing today to progress in the open source front, to making models that are better and better. And we've also opened what we call the optimized models, some commercial models around a platform that serves them. It's very similar, I guess, to what many people are doing, except that we propose a platform that is portable, that can be transparently deployed. So that means that we can bring the platform, we can bring the model weights for them to be modified, for our customers to modify them, to fine-tune them. And we have made a variety of strategic partnerships with cloud providers, but also with NVIDIA. That's something that we announced, that Jensen announced on Monday. And I think the mission that we have is to bring the AI to everybody. So make it small enough so that it runs on laptops, make it good enough so that it reaches the best reasoning performances, and also make it portable enough so that enterprises, developers can basically work where they're used to work. So that can be on cloud, that can be on our platform, that can be on private cloud, that can be on-prem if needed. And oftentimes it is, as usually what you do with generative AI is that you work on your proprietary data, and so there's a lot of compliance aspects to it that we think that has pushed us to make a portable platform. So we do offer like 5 models for all use cases and business needs. So Mistral 7B, Mixtral, but we also have this small model which is actually performing better than Mixtral and with lower latency. And we have Mistral Large, which is currently within the top tiers model in terms of reasoning capacities. We've worked so beyond the scientific effort that we did until December. We started to work on adding new capacities to the model. So it is now multilingual. It has function calling. Function calling is actually quite important in today's application when you make agents, when you make your model interact with databases, interact with tools. We have this JSON mode that allows to force the model to output something that you can then use to call an API. And we've optimized for what we call RAG use cases, so really optimizing for the model to be able to think about the entire context it sees. We also have an embedding model that we did in December, which used to be state-of-the-art, but which is still pretty much state-of-the-art. It's a very fast-moving field, even more than in the large language models. And yeah, everything is available through our platform, and it's progressively available through a variety of partners. It's also available on ai.nvidia.com now. So yeah, I guess that's this I already said. And in terms of, yeah, as I've said, in terms of performance, we have been optimizing, including for Mistral Large, over like the latency, over the capacity of the model to make it small enough with a certain level of performance. So today, Mistral Large has a quite low latency compared to others, and we will continue bringing this compression aspect to our technology, because we think that this is the way in which complex applications can be made. The reason why like latency matters is that once you reach a certain level of latency, so through better hardware, better models, you can start thinking on how your AI can run on the background. So instead of having just assistants that are talking to people, you can have assistants that think on themselves at a sufficient speed so that you can create applications with a good user experience. So this is really something that we're optimizing for. We've optimized for privacy, as I've said. We don't track your inputs. We optimize for security. The custom deployment, VPC deployment, is basically as secure as you can get. We have optimized for guardrailing, so you can define what is appropriate for your specific use case. You can set basically the guardrails you need in the prompt, and we ensure that those are respected. And because we have been curating our data pretty well, we have a very strong bias control, so that our models demonstrate actually top-level performance when it comes to gender, religion, politics, and bias and ethnicities biases. And so I guess those are basically our core proposition. We intend to be the leader in open source, and so we're currently serving the best open source models, and our intention is to continue doing so in the coming months. We have better models coming. We have new capacities coming. Multilinguality is something that is quite important to us and that we're pushing forward. And as I've said, the idea of being open and having very strong open source models is also to enable our customers to modify the model and to fine-tune them to their use cases so that they get better performance, so that the model actually adapts and get better over time. So this is also something that is coming to our platform, to which we will bring our expertise and AI expertise. The idea being to lower the bar of admission toward the fine-tuning models, and so this is coming. I'm not announcing dates, but this is coming pretty soon. So thank you, everyone, and I'm happy to take any questions.
Thank you very much, Arthur. Thank you very much, Arthur. We do have time for a few questions. If you have a question, please step to the microphone that's in the aisle over on that side of the room.
Are you guys using any synthetically generated data in your models or model building?
Yes, we do to a certain extent.
I thought so. That's all. Thank you.
So I want to bring something back to a paper you'd worked on, the retro transformer DeepMind. You guys were doing retrieval augmented generation before it was cool. I was wondering if you, and it was integrated itself in like cross attention in the architecture. I'm wondering if you see that as another method going forward to integrate retrieval augmented generation directly in the architecture or agents directly in the architecture. I want to get your thoughts on that.
Yes, so I think that's so. Retro brought a couple of architecture innovation and training innovation. Some of them were good, some of them were not good. In particular, training on like pre-training with retrieval augmented, well, basically with neighbors is a good idea and a bad idea, because it's a good idea because your model actually understands how to retrieve from documents, but it's a bad idea because it makes the task much easier, because your model now sees much more context, and so it doesn't need to try to memorize things as it would if it didn't have access to retrieve documents. So I think in that sense, I don't think we cracked it, and nobody has ever since. On the architecture side, the encoder-decoder models that actually process documents separately, I think these are pretty exciting stuff. This is pretty exciting. It's a pretty exciting paradigm. It's very close to what we propose for Mistral 7B, which are sparse attentions. Sparse attentions is also basically another way, a more flexible way of having encoder-decoder structure. And I think this is also a very promising aspect to the architecture development we'll see in the coming years.
Okay, thank you very much.
Hi, thank you for your speech. I wonder, do you plan to come up with an LLM in French language from scratch, or are you guys planning to stick with the translation LLMs? And if yes, how different is the process for the French language?
It doesn't seem to be a great idea to train models on a single language from scratch, in particular for languages that are rarer than English. So this is not what we do. Our models are multilingual by design, and I think that we have evidence that there's some transfer in between the languages. So if you want your model to be very good at French, you need to train it on English a bit.
Okay, thank you.
Okay, thank you for the great talk. So I have some question about the MOE architecture. So did you find some scaling laws specific for MOE, and why did you choose this architecture? And also the Grok 1 appears, but it's also in MOE, but it's not as efficient as Mixtral. So what do you think of it?
So MOEs and have some different trade-offs. They're very good at processing a lot of inputs. They're a little worse at outputting tokens, because you need to load basically all of the experts every time you output a token. So there's some trade-offs. It depends a bit on the workload you have. Generally speaking, they're quite efficient for training. Then I know that some of our competitors have trained very large models, very large MOEs. Well, it's not all about the size, right? It's you also, as I've said, there's also some questions on how do you set things up so that you get something that is compact and has a lot of knowledge. And so I'm not sure why our Mixtral is as good, but it is good enough. Yeah.
Okay, thank you.
Thank you very much, Arthur. That's all the time we have for today.
Thank you.
Enjoy the rest of GTC.